Hello, everyone, and welcome back to another episode of Solidity Fridays. Today, I'm joined with my co-host Gareth Larken, another Solidity developer, and we have a very special guest. We have Optimizer with us, who's also known as Vectorized. Thank you for joining us today.
Hi, Tamara. Hello, Gareth. Hi, Michelle. Thanks so much for having me here. Pleasure to meet all of you. And hello to all my viewers. Hope today we will have a good time. Okay.
Thanks for coming on.
Okay. Yeah. Okay, so without further ado, I will try to present a bit of the dark arts of you. Why it's called dark arts? Because next slide. Yeah. Okay, next slide. Go to the next slide. Yeah, okay. So before we go to the dark arts, I have to say a disclaimer that some of the stuff here may be not accurate. Yeah, so nothing here is supposed to be taken as advice, and if anything goes wrong, we do not give any warranties. Okay, without further ado, next. Okay, so most of you probably know me as the maintainer of ERC 721A, and I also have another. Oh, okay. Yeah, and so there are two repos that I mainly maintain. First is 721A, which is the guest optimized 721 implementation. And the second repo I created to complement ERC 721A, which is Solidity. So Solidity is a collection of highly optimized Solidity snippets, mostly written in assembly, or you can call it YUL. Next. Okay, so why we want to use U? 3 points. First is flexible. Second, we want to save gas. It's fast. And third, it interoperates easily with high-level solidity. So there is other languages like Half, or you can write in bytecode if you are very familiar with it. But it's not so easy to use them in the context of higher level code. And also, if you want to verify on Ether-scan, it's a bit difficult if you are not using U. Okay, next.
Interesting. I didn't know that about Huff. That's very interesting to know.
Yeah. Okay, so many people ask me, what resources do I recommend for you? Off the top of my head, I can recommend 3+1. Okay, 3+1. Actually, 2. Okay, the two most official ones are the EVM.codes. This is like a Bible of all the opcodes used in the EVM. And they also give some extra information, very useful extra information about the EVM. The second most important is the Solidity length U documentation. This documentation sometimes will have a bit of minor updates from time to time. But yeah, it's quite important. So the first two are important. The third is my repo, Solidity. So there are sometimes where you prefer to have examples to guide you along your learning process in U. And you can visit Solidity for many different kinds of examples. And the last but not least is Remix. Okay, yeah. So many people have the misconception that Remix is a beginner tool because yeah, we have Hardhat, we have Foundry, very advanced, very powerful tools. But Remix offers a very special function called the debug functionality. So it allows you to view the stack, allows you to view the memory, allows you to view the bytecode. And this allows you to figure out how Solidity or how U is being transformed into the bytecode. which helps you understand what is behind the scenes. So you can see I tweeted something about remix. T11S also tweeted something about remix. The person who wrote this is not me, it's someone else. And another very goated developer, Ross Campbell, also tweeted something about remix. Yeah, so remix is pretty useful if you want to learn Vue. Okay, let me talk about the philosophy of how I approach Vue, because we can talk about the technical details, but I would like to show how I think about it. So to make an analogy, I would say Vue is quite similar to a martial art, because often you will have examples where a single opcode can achieve multiple objectives. It's like attacking and defending in a single move. Vue is also quite similar to bonsai, because the EVM is quite a constrained environment. We are working in constraints. But these constraints, if you view them in a different lens, you can turn these constraints into opportunities. The imperfections become a form of artwork itself. And third is freestyle. Like after you learn the basics, it's really up to how you play by the tune, how you ad-lib, how you combine various computer science or maths knowledge picked up along your life and combine it into a code. So it's about freedom, it's about creativity, about improvisation. Okay. Yep. I tweeted something about it too. Okay, next. Okay, oh, is this the old one? Okay.
Oh, sorry, is there a new thing to...
Oh, wait, hold on. Because I think I reordered the slides, because I decided that if we suddenly go into the examples, it might be too sharp of a jump.
Okay.
Okay.
Cool, I'll share the new one.
Okay.
So Optimizer, do you mostly code in Yule? Do you find it easy now with Solidity?
Okay. Just a warning, a heads up. Okay. If you code too often in Vue, you will start thinking from the perspective of Vue when you approach a problem.
Yeah.
And you'll feel more comfortable coding in Vue than Solidity after a certain time. And that can be quite a nuisance if you're working in teams, because sometimes you find that it's so much easier to code in Vue than Solidity. You just don't want to try the Solidity way. Yeah.
Okay.
Sometimes.
So you'd prefer to code in Yule, but sometimes in teams you have to still use Solidity.
Yes, because yeah, you get it.
Okay.
Yeah, maybe soon everyone will learn Yule and then you'll get what you want.
Yeah,
Cool.
hopefully. Okay, yeah, so oh yeah, so if you know a bit of Solidity, hopefully you can understand this course. Okay, next. It's not a full-fledged course, it's more like a gentle introduction, hopefully gentle. Okay, next. Okay, so before we go into the examples, in case some of you, I know some of the audience are Vue experts down here. They're just watching for fun, but I think that there is a significant portion that are quite new to this Vue landscape. So I will try to give a hyper compressed crash course. Okay, in Vue, every variable is a uint256, okay, or bytes 32. So 256 bits is 32 bytes. So the idea is, if you only have one type, you don't need to type check. Yeah, there's no need to care about type safety if there's only one type. which is the U in 256. Okay, in U, arrays can exist in storage, memory, core data, because it's the EVM. That's the storage, the memory, and core data. And you expose all the inner workings to U. So how you access them is quite different. It's different for storage, memory, and core data. In Solidity, it feels like the same. You just use the square brackets, but in U, it's different. It's very different, okay? In U, you have to manage memory manually. So what I mean by manually, you have to know some kind of ground rules. So in the EVM, you have the memory, and the memory is divided into slots. Each slot is 256 bits or 32 bytes. So slot 0x00 and 0x20 are the first two slots. They are what we call the scratch space. That means you can do whatever you want with it. Slot 0x40 is the free memory pointer. So this slot holds a number that points to the slot in memory where it is the free memory. That means the part of memory that hasn't been allocated yet. So to allocate memory, you just have to grab the value from here, get the value from here, add how many words you want, and then write back the outdated value. Slot 0x60 is some kind of forbidden slot, which values, you have to somehow set the value to 0 always. So the value by default is 0. It's not recommended to write to this slot, but if you ever want to write to this slot, you have to remember to set it back to 0. Okay, and there is a lot of manual things. You have to manual storage management, manual event emission, manual everything. So it makes you feel tedious, but after a while, you start to get more confident in what you do. Okay, next. So before we go to examples, let's do some warm-up. So let's start with the most simple thing you want to do in U, or hopefully the most simple. Let's write a loop. Okay, next. So let's try to write a function using U to sum up an array and return the sum. So this is the straightforward implementation. Okay, let me explain a bit. In line 4, we use this thing called mload. Mload is memory load, short for memory load. So you load the first slot of the memory, which contains the length of the array, how many elements are there in the array. And then you have this familiar for loop syntax. So you start I equals to 0, and then I less than the length, you I plus plus, and the results is simply you add the value at the array, the element array, to the result. Okay, so 0x20 and all these 0x20. So 0x20 is 32 in hexadecimal. Every word in Solidity contains 32 bytes. So you have to add 32 every time you go to the next element.
So are the creations of the functions, so like line 2, basically exactly the same as Solidity?
Yeah.
Okay.
Okay, there is pure U and there is Solidity mixed with U. They are almost the same, but I recommend using the Solidity plus U.
Okay.
Yeah, so that you can interact with your higher level code.
I see. Awesome. Let's keep going.
Okay, so can we make this loop faster? Okay, next. Oh, we managed to save a few guesses. So in Solidity, it's quite counterintuitive. If you go to a previous slide, you will see that there's a less than. But now we have a is 0 and equal in the Boolean condition. Okay, but it costs less gas. How come? Because behind the scenes, Solidity actually will remove the is0 in the condition if it is there. But if you do not have the is0, it will add a is0 down there. Yeah, so this is like the subtleties of view. This also explains why in Solidity, if you use a not equal, sometimes it's faster than a less than. Okay, next.
That's so interesting.
Yeah. Oh, what did I do here? Oh, we did something simple. We just cache the n instead of computing it every iteration.
That surely saves a lot of gas.
Yep.
Yeah, I would think so.
But when you cache the n, instead of adding 1, you have to add 0x to 0.
Okay,
So you have to add 32.
Yeah, that makes sense.
Okay, so next. Wait, what did I do here? Oh, I replaced the multiply with a shift left. So multiply by 32 is equivalent to shift left by 5, SHL. Yeah, you managed to save, I think, 2 gas or 3 gas. It's a tiny optimization, very tiny optimization.
It's very interesting.
So, yeah, sometimes shift left may not actually save you gas because, shift left, the order of the elements matter, whereas add is commutative. You can switch the order of the elements and it gives the same result. So sometimes Solidity needs to reorder the stack elements if you use shift left, which makes it cost the same gas as add. But usually you can save like 2 or 3 gas if you use shift left.
How do you know when it's whether or not it's gonna save gas? Do you just have to look at the variable?
You have to use your gut feel and you have to test.
Okay.
Yeah, it's a dark art. It doesn't always work. Okay. I think there's still more. Oh, okay. This is a special trick. Okay, so previously we used a regular for loop, but now we convert the regular for loop into an infinite loop, but we add a condition to break out of the loop. So it actually, wait, did it go up in gas? I think it went up in gas a bit, but never mind. It will go down in gas after I add in some tricks. So okay, right now, okay, previously I store the m load a into a temporary variable called n, but right now I just duplicate the operation on line 4 and line 5, m load a. So I just load the length twice. Okay, here is the thing about you. Sometimes during repeated operations, might save gas over caching the operation. Because when you cache an operation, when you cache it in a variable, it actually creates an extra stack variable. And because of the extra stack variable, they have to do some stack juggling, which might cost gas. So in this case, if the operation is not too complex, sometimes you just copy and paste it twice. Yeah, you can go back to the previous slide and compare. Yes, I think it saved like 3 gas or something. Very little gas. Yeah. So the next trick is replace the equal with a is0 less than. It save you even more gas. So right now, if you compare with the regular for loop, I think it's cheaper than the regular for loop. But this trick doesn't always work. Okay, sometimes it works, sometimes it doesn't work. And the final trick is replace the memory with a core data. Yeah, so if you compare how I load the memory and how I load the core data, it is quite different. In the core data, the first element is the first element, okay? But in the memory, the first element is actually the length. Yeah, so the semantics is quite different if you use memory versus core data. Okay, until here, any questions?
No questions from chat. Although someone did say earlier on when you were still going through the basics that it was more efficient to do what you're doing here in the last slide. But I kind of knew that we would get there. So we got some people in the chat that are also very much optimizers. So yeah, keep going. This is great.
Okay, next. Okay, so this is some tricks in U. There is no if else. So the closest thing we have is a switch statement. So here is a very basic example of how you create a switch statement. Basically, you pass in. Okay, we're trying to make some kind of lookup down here. You pass in I, and based on the value of I, it sets the results to what we want.
It's very similar to like a normal Web 2 language, like Java or something.
Yeah. Okay. Next. Okay, so now in U, there is no concept of early return. Like, you know, in Solidity, you can halfway through a loop, you can return, and then it like terminates the whole thing or skips the rest of the stuff. But in U, the closest thing you can do is something like that. So you do an infinite loop, but then you do the if something then break, if something then break, if something then break, if something then break, and the final you have to also put a break at the end. So this simulates a if else kind of structure.
So Tamara, just go back a slide quickly. Can you not put break after in the cases as well? So after that result, like case 0 result break.
Okay, in Solidity, okay, in U, the case always breaks no matter what.
Sorry, I lost you there.
Okay, sorry. In U, okay, in assembly, the case doesn't flow to other case. So once it computes the case 0, it automatically skips the rest.
Oh,
it
so
will
it
skip
breaks
all the
automatically.
rest. Yes, it breaks automatically.
Okay, thank you.
Okay, this I think is save one guess. So it's quite equivalent to the previous example. But okay, this one actually save a bit more guess than the first example. Yeah. So it's quite strange how U actually works under the hood. Okay, and one last thing before we jump to the examples. Okay, I need to caution that in U, you have to be very careful with the upper bits of variables when the variables are less than 256 bits. So for example, this is the demonstration. We pack the address, which is 160 bits, with some kind of timestamp into the storage. If you do the computation in plain Solidity, yeah, it returns true, which is what we expect. But if you try it the straightforward way, the naive way in assembly, yeah, you find that the function returns false, which is not what we want. Does it surprise you that this function actually returns false? Because you will expect that casting the address actually clears the bits, upper bits, but it doesn't. So this is a very important lesson on you. You have to clean the upper bits manually. So the third line is the third function, caller is stored assembly correct. It shows you how to clean the upper bits. If you do not clean, the upper bits are not clean. So how to think about it is that in Solidity, when you do casting, the variables are not actually clean on the spot. They are only clean when you assign it to a value or use it in the comparison. It's clean on the fly. It's not clean on the spot. Yeah. So this is something you have to be very careful if you are using U to do manual packing. Okay. So do you understand what 26 do? So it basically shift left by 96 and shift back by 96. So it cleans the upper 96 bits. So 96 plus 160 is 256. So you basically shift left and shift back. And all the, yeah. So next, okay, we can also do a mask instead of a shift left and shift back. And surprisingly, it costs the same gas. Oh, how come? Okay, because the compiler did some stuff behind the scenes. Okay. Sometimes masking costs less gas. Sometimes shifting left and shifting right costs less gas. There's no hard and fast rule to it. You have to play and you have to try profile. Yeah, it's not always one way is better than the other. Okay, next. Okay, now is something surprising. I try to mask the caller and somehow the gas stays the same. How come? It's because the compiler understands that the caller is a source that has clean upper 96 bits. That means if you use caller, the compiler understands that masking it doesn't do anything to the upper 96 bits, which are clean anyway. So the compiler can optimize this masking away automatically. Next, if you do the shift left and the shift right trick, the compiler also understands what you're trying to do. So it will also optimize the masking away, giving the same gas. Quite surprising, the compiler. Okay. So next. Okay, so talking about the safety, if the source of any variables is less than 256 bits or less than 32 bytes, 256 bits is 32 bytes, you should clean the upper bits if required. Okay, if you're writing library code, but if you're doing something for Solidity, it is a good practice to return clean variables from you if possible. That means if you're trying to return an address, you might want to consider cleaning the upper 96 bits before returning it. But it's not always necessary. Third is when you use booleans in U, if you know the source and the source is either 0 or 1, like from a Solidity conditioner, you use a boolean in Solidity, it will generate either a 0 or 1. Or if you use a greater than in U or less than, it also generate a 0 or 1. But sometimes people use a non-zero value to denote a truthy value. So if you know that some people might actually do some stuff before they pass in the variable, it's better that you clean the variable. If it's a boolean, you cast it to either 0 or 1 before you use it in your boolean logic in U. And in testing, you should do all the brutalizing stuff. So all these are just like for safety, because we want fast, but we also want to. But before we can be fast, we should focus on whether we can be safe. Yeah. If you are fast but not safe, that's not a good thing. So in U, you have to be a bit more careful. Actually, much more careful, yeah. Okay, so we know that compilers sometimes quite smart. Yeah, but sometimes the compiler is quite unpredictable, and sometimes the tricks work, sometimes they don't. You have to test. Yeah. Okay, so now I demonstrate on 3 examples. Hopefully, they are not too complicated. So previously, I talked about how U is like a martial art. Like one operation can have multiple objectives. So for the first example, I will use the ECDSA library in Solidity to demonstrate this. Okay. Okay, in this so-called, let's call this demonstration artwork. Okay, artwork. So there are 3 tricks we use here. Okay, 3 main tricks. First is we use slots clobbering. Okay, what is slots clobbering? I don't know who came up with this term clobbering, but basically it means that if the scratch space is too small, you might want to use the free memory pointer and the 0 slot, or even more, to store variables temporarily. So if you want to use the scratch space and you want to use a zero slot, you have to cache their value into temporary variables, like in line 6. Copy the free memory pointer so that we can restore it later. Yeah, this is what we call slots clobbering. You cache the value and then you restore it after you have done all your stuff. So we restore it in line 32. Yeah, this is called slots clobbering. We also restore the 0 slot in line 27. Yeah, you have to restore the 0 slot and the free memory pointer slot.
What happens if you forget to restore the 0 slot?
Okay, your code may give errors like out of gas errors or weird stuff. It's undefined behavior.
Okay.
Yeah. But if you forget to restore the free memory pointer, usually you will get an out of gas error. Usually.
Okay.
Okay. One hidden trick here is we don't need to check whether V is 27 or 28. So in ECDSA, V is the version of the ECDSA you want to use. So if you look at Open Zeppelin's code, they will have this V equals to 27 or 28 check. But based on recent findings through optimizoring, we realized that the pre-compile, the EC recover pre-compile, actually checks that V is 27 or 28. So we use this knowledge to remove this check. Yeah, because we understand how EC recover works under the hood very well, we know that it's safe to remove this check. So this is part of the general knowledge. Okay, and the last point here is that we abuse the need to restore the 0x6020 to eliminate opcodes. Okay, how to explain this? So we know that we have to set 0 x6020 after we use all the stuff. Some people see this as a burden, like an extra step you have to do. But if you look at it a bit closer, you can see that it provides an opportunity to remove some opcodes. So the idea is we know that after restoring it to 0, this slot will always be 0, okay, because it's 0. And we also know that the written data size is either 0x20 or 0x00. Okay, so we can abuse this to somehow remove an instruction by loading the slot. Yeah, so if it's success, it will load the slot where the output is. If it's a failure, then it will load the 0 slot. So in this way, we skip an operation or 2 operations. Yeah, so this is the concept of how you can use one opcode to achieve 2 objectives.
Yeah, that's cool.
I don't know whether
That's cool. That's like the attack and defense that you were talking about in the martial arts.
It's a bit okay. You have to visualize it. But it's quite involved. Yeah, it's quite an involved thing. It's quite an in-depth thing.
Yeah, it is.
That's why I call
awesome.
it dark arts.
Yeah, that's a good way to call it.
Okay, next is okay. This is a more advanced version of what we call the slot clobbering. Okay, so this is a function that deploys a minimal proxy. So after deploying a minimal proxy, we have to restore the part of the free memory pointer that has been overwritten. So the straightforward way is you cache 0x40 in a variable and then restore it. But we know that only part of it is being written. And we also abuse the fact that for all practical purposes, the upper bits of 0x40 is always 0 because of the thing called memory expansion cost. So we can abuse these 2 facts to directly write 0 to the upper bits of the free memory pointer instead of caching it and then restoring it from a variable. Yeah, this is some very in-depth stuff. If you don't understand, it's okay, don't worry about it. This is a very rare use case. Okay, so this is the famous safe transfer lib. So safe transfer lib is a library in Soulmate where it allows you to do ERC20 safe transfers in the efficient and safe manner. That means you don't need to worry about stuff like the return values is inconsistent and so forth. Okay, so for a long time, people thought that, oh, this is kind of the best we can do. But after a while, if you look at closer inspection, you realize that you can abuse some tricks to remove even more operations. Okay, so first, there's both examples use slot clobbering. That means we cache the free memory pointer and restore it later. Okay, but the second example, which is in a PR to Soulmate, abuses some trick, okay, to simplify the Boolean condition. So on the left, you have to like compare return data size is larger than 31 and so on and so forth. But on the right, the Boolean condition is much simpler. So the thing how to exploit is we notice that the function selector doesn't end with 0, 1. So we write it to the 0 slot. And we know that in order for it to be success, it has to return at least 31 bytes, that means 32 or more. And it has to return 0, 1 as a return data. So the only way this can happen is that it returns 32 bytes and overwrites the DD, the last byte of the function selector. And based on this reasoning, we can remove the greater than return data size 31. And this also reduces the bytecode size because we don't need to store the super Dutch number, we only need to store the last 1, 2, 3, 4, the 4 bytes, the last 4 bytes of the number of the function selector. So this makes it more efficient and also save the bytecode size. If you want the full reasoning, you can visit this link down here to the PR, the pull request. Yeah, there's a full reasoning down there. Okay, next. And finally, we have the Merkle proof. Okay, so previously we learned that sometimes the infinite loop with the break trick is more efficient than a regular for loop. So we can see this in practice down here. We also use some bitwise tricks to avoid branching down here. The regular version of Merkle proof verify, they will check the condition, and based on the condition, it will swap, do a if, and then swap the variables, and then do the hashing. But down here, it does some XOR stuff. Okay, you can look at this code later if you have time. Okay, next. Okay, so just some general tips. Okay, when you write functions in Solidity, sometimes the compiler can inline the function for you. That means it removes the function call overhead by copy and pasting the bytecode for you. But there are some criteria. First, the opcode must be small enough, not too many opcodes. I don't know how much is small enough. I don't know what is the threshold. But second is the important thing, which is the function does not have branching, even in U. So if you use any if in U or any for loop in U, then the compiler won't inline the code for you. So this is just something to keep in mind. Okay, and yeah, some other general tips. Okay, sometimes Solidity or a mix of Solidity plus U can actually outperform U alone. So too much of a U is not a good thing sometimes. Yeah, you have to know when Solidity plus U can be faster, because there is high-level information in Solidity that can help the compiler do optimizations that just looking at the low-level semantics cannot perform. But you have to combine high-level and low-level information for the compiler to do some kind of optimizations that, yeah, they are more worth it. You can abuse bytes for lookup. So there's a opcode called bytes in U, which is quite useful if you want to do a lookup in. Okay, I will have an example later for demonstration. Okay, and the third one is, okay, you have to know your personality type. I know this is kind of a voodoo thing. Some people don't believe, but I think that, yeah, you need to find out, like, are you a thinker or are you a feeler? So how I think about, okay, I don't actually really think about you. I feel about you. So, yeah, depending on what kind of personality, you should structure your learning process in a way that suits you the best. Okay, and just some general advice on programming Solidity. And also, yeah, you have to have fun. If there's no fun, then what's the point of it, right?
Thank you. Those were amazing tips.
Yeah. Okay. So, oh, this is to demonstrate what I mean by bytes. Okay, so now we have a algorithm to calculate the least significant bit of X. So if the bit, the most, okay, the rightmost bit, sometimes people call it the least significant bit, sometimes people call it the rightmost bit. But anyway, we want to return the least significant bit. So this is the common way of doing it. But if you use bytes lookup, and you combine it with some math knowledge, you can perform some optimizations. I think it's about 50 gas cheaper or something. You go to the next slide. Yeah, so this is what I mean by you combine this and that and just mesh stuff together. So byte is performing a byte lookup on this giant number. So and it used some kind of trick called the Bruegin lookup. You can visit this webpage for more details. So bytes is basically you find the 8-bit number in a 256-bit number starting from the left. So byte 0 of this number is 0, 0. Byte 1 of this number is 0, 1, and so on and so forth. So we abuse this opcode to treat a number like a 32 slots array. 32 slots array of 8-bit numbers. Yeah, basically byte is like you take the character at the position. It's yeah.
It's very cool.
Okay. Then next. Okay. People ask me how to learn U, and sometimes people also ask me how to master U. Okay. But I can only quote Bruce Lee, like you just have to practice, and after you practice, you just have to internalize what you have learned, and in a way you forget what you learned, because if you have done anything about like AI and stuff, you will know that actually forgetting is part of learning. Like you make it second nature such that you don't need to actually remember or think about it. It just comes as it is. So if you don't really understand, what I say is just try, just do, and hopefully after enough trying, it becomes like second nature and you don't need to try. Yeah.
Yeah, like you said, you start to feel it instead of think about
Yes,
it.
start to feel it. Don't think too much, just feel it.
That
But
sounds
if you're a
amazing.
thinker, think about it. Yeah, depends on your personality. Some people are better thinkers, some people are better feelers.
Yeah, I'm a thinker myself.
Yep, so we still have some time actually. You want to ask me any questions?
I have a question. And I asked you this privately, but I want to know if you can maybe explain it more. Why in ERC 721A is there a struct with one variable in it?
Okay. Can you visit the 721A repo?
Sure.
Yeah. Because that I found very interesting.
Okay, you click the contrast.
Yeah.
I think I added a comment. Okay.
Down there.
Yeah. It's a bypass for a bug. So some backstory. Okay, the backstory is like that. Previously we used some manual slot calculation, but when we pass in the mapping as a storage variable, like you can put mapping of uin 256 to uin 256 blah blah storage. Somehow if we do that and we compile with this vr dash vir, it will have a compiler bug. Like it just doesn't compile. It will like terminate with an error message. So after some inspiration, we thought of simply wrapping the value in a struct, in a one variable struct, and use this struct as a reference to the storage slot. Okay, so in Solidity, there are primitive types and there are reference types. Reference types are like structs, mappings, arrays. Yeah. So what I mean by reference type is that you can put something variable name space storage inside your code. So we want to put token approval ref something storage. So this is how we can do it. If we do not wrap it, the compiler just doesn't want to compile. And yeah, VRIR is quite troublesome. I wouldn't really recommend using it. Like sometimes it doesn't really help much. It makes a compiler like recently there's one VRIR, but I can't remember the specifics of it. So, but anyway, we just want to maintain widespread compatibility. That's why we add this bypass in.
That's interesting. Yeah, that's crazy. That's some seriously forward thinking.
Yeah.
Someone asked about the factorial example. I'm not sure if I missed that, or if that's
factorial example.
Okay. Yeah. So for the factorial example, you have to visit Solidity repo. Solidity repo.
cool. While we wait, yeah, if anyone has any other questions, please just ask it in chat, and then we can ask Optimizer while we've got him for another 6 minutes.
If you want to ask me after these 6 minutes, you can always DM me on Twitter. Okay, so under source, utils, fixed point mathlib, yeah. So under here, there is a certain function that doesn't use u completely. Actually, it's completely in Solidity. You control F factorial, control find factorial, or you can just scroll down. Yeah, so this is a plain Solidity function. So this is what I mean by know when pure U performs better and know when pure Solidity performs better. Yeah, so part of mastering U is that you need to know when to use it and when to use something else instead of U.
So how do you know? Like, do you just play around with it and just understand what is?
Yeah,
more?
is it just through testing? Or
Yeah,
is it, have you tested enough now you actually have a feeling you can be like, oh, actually, here it'll be more efficient?
Yeah. After you have programmed enough, you will roughly know, have a gut feel of when it's more efficient. Okay, like for example, there is I think there's a function called LNWAD, LNWAD. LNWAD. Yeah. So this function is written by T11S, and here. So it is in, okay, this part is in assembly, but the rest are in pure Solidity. Just uncheck. You scroll down a bit more. Okay, here, this part is in U, but here is all in Solidity. And if you actually try to rewrite this in U, you'll notice that the gas actually goes up. Yeah, so the Solidity compiler actually is very smart about this kind of highly like math-heavy operations that don't have loops. So if it doesn't have loops and okay, maybe simple loops and mostly plus minus times divide, yeah, this kind of simple math operations, one after another. Usually, Solidity alone is faster than U, usually. So, yeah, you have to get an intuition of when U is faster, when Solidity is faster. It's quite weird.
Yeah, it must be quite confusing.
Yep.
But it's good to know, good to learn, and good to get a feel for.
Yeah, that's why it's an art. It's the art.
Yeah, absolutely. Gareth, are there any more questions in chat?
No, not at the moment. So I think we could probably wrap up.
Yeah.
Yeah, I think from our side, that was very, very cool. And I know everyone in chat enjoyed it, and I'd really suggest following Vectorized, also Optimizer on Twitter. Things that, well, the tweets are really cool and very informative. So yeah, it's been quite a privilege to also learn from you and see this PowerPoint and just understand a bit more of the dark arts. So yeah, thank you for that.
Yeah, thank you so much.
You can share the tweet. Okay, the Google Slides, Google Docs link.
Oh, sure.
Google
Cool.
Docs.
We'll share
Yeah,
that.
you can share it. Okay.
Thank you.
Thank
Yeah.
you.
Thank you so
Nice
much
to
for
meet
joining
you.
for another episode of Solidity Fridays. And thank you so much, Optimizer, for being our guest.
Yeah, that was amazing.
Thank you.
Thank you.